Okay, so this one is on some MI. It's from the OCR A levels, and this one's a little bit challenging, but honestly, if you know how to do it, it'll be quite easy. So part A is just a Christmas gift. Sorry about that. Hold on. Part A is a Christmas gift. We want alpha plus beta and alpha beta, which is negative b over a is 1. And then alpha beta is c over a, which is negative 1, and that's it. Part B1 wants to find S2 and S3 respectively. So S1 is alpha plus beta, which is just 1. S2 is alpha squared plus beta squared, which is alpha plus beta squared minus 2 alpha beta, which is just 1 squared minus 2 times negative 1, which is 3. S3 is alpha cubed plus beta cubed, which is alpha plus beta, alpha squared minus alpha beta plus beta squared, which is just 1 times 3 minus negative 1, which is 4, because this is 3. And that's part B1, answered pretty quickly. B2 is the MI part. So we want to prove that Sn plus 2 is equal to Sn plus 1 plus Sn for all n belongs to the naturals, and n is greater than, it's just naturals, and n is greater than or equal to 0, which is just natural numbers. Here we already have P1 proved, in fact. So when n equals 1, we have left hand side as S3, which is 4. Right hand side is S2 plus S1, which is 3 plus 1, which is 4, which implies P1 holds. And then assume this is just basic MI. i.e. sk plus 2 is sk plus 1 plus sk. When n equals k plus 1, LHS is sk plus 3, which is alpha k plus 3 plus beta k plus 3, which is alpha k plus 2, alpha plus beta k plus 2, alpha plus beta. Just creating stuff out of nowhere, basically. The concept of adding 0. Here we have minus alpha k plus 2 beta and minus alpha beta k plus 2. Well, this is because that way we could create sk plus 2, and maybe we could get sk plus 1 here, but we don't know. But for sure we're getting sk plus 2 now. And then minus alpha beta, we have alpha k plus 1 plus beta k plus 1, which is S1. And then minus alpha beta is just minus negative 1, which is just sk plus 2 plus sk plus 1. And we get RHS, which implies this holds when this holds, which implies Pn holds for all n is in the naturals. And that's part B2, one of the harder parts of the question. B3 is, you could prove that by intuition. So we know that S3 is S2 plus S1. And Sn is equal to, n plus 2 is equal to Sn plus 1 plus Sn. And then, which implies Sn, maybe I should write it the other way around so it's clearer, is equal to Sn minus 1 plus Sn minus 2. which implies you could see that Sn is equal to lambda S2 plus mu S1 for lambda and mu belongs to the integers, which implies Sn also belongs to the integers. And yeah, that's it for part B3. C1 wants to explain why Tn is unsuitable for the sequence. So we know that alpha n does not belong to the integers, because alpha is not an integer. We couldn't get alpha n as an integer as well for every n is greater than or equal to 1. So yeah, for all n belongs to integers. Oh, in fact, I should just say for some, because there could be a case where alpha n is actually an integer. So I could say sometimes it doesn't equal to it belongs to the integers. So yeah, which implies it's unsuitable. C2 wants us to formulate a Tn such that it's not alpha n plus beta n, or else it will be the same and everyone will get these 2 marks. So this is the hardest bit by far, and obviously we could use the floor function at this point. That's what I'm thinking. Okay, you know what? Let me try. So alpha is... Obviously, we could go ahead and solve the equation. So x is so which implies alpha is because we have this. Now we could say alpha 1. Oh, sorry. Floor function of alpha is a floor function of 1 plus root 5 over 2. 1 plus root 5. So root 5 is 2.236 plus 1 is 3.336 divided. So we get 1. Which is equal to alpha plus beta. Floor function of alpha squared plus 1 gives us 3. I've done these calculations beforehand, that's why I'm so fast. Gives us 3, which is equal to alpha squared plus beta squared. Alpha cubed gives us 4 floor function, which gives this. And through recognizing patterns, we could say not Tn. We could say that Sn. I wouldn't do this by induction because the question only requires me to state a multiplication, not to prove one. So I'd say just alpha n plus 1 floor function when 2 divides n, and alpha n when 2 does not divide n. So that's my answer for part C2, just using the floor function. And I recognize this pattern, so I'll just go ahead and do that. And that's it for this question. Very interesting.